Hello, everyone. Good morning. Welcome to this workshop organized by the GeoConnect3d project. And this is a side session of the Geoscience Policy and Society event happening this week. My name is Renata Barros. I'm from the Geological Survey of Belgium, and I'm the project coordinator. And it is my pleasure today to be with you while we show a bit of our project. And before I start, I would just like to let you know, you watching, that you are muted in listen-only mode, so you don't need to worry. But that you can interact with us, send your questions using the Q&A box that is on the bottom of your viewer. And as you see in your welcome message, there will also be some interactive polls. So I will give you the instructions later on when is the time. And also, I will ask our speakers of today to turn your cameras off when you're not presenting, so that the audience can have a better view of the presenter. So GeoConnect3d, sorry, so sorry, I'm having some trouble here, sorry about that. So I want to tell you a bit about GeoConnect3d, of course, before we jump into the discussion and results. So this project has one very ambitious goal: to prepare and disclose geological information in a new way, in a different way, in a way that we can better support policy needs, especially those related to subsurface management. And we are motivated to do so because we know that to achieve the greener, more sustainable future that we dream of, we, as society, we will rely more and more on the subsurface, its resources, and its potential. And when we talk about managing all of these extended and new uses that will appear, geological knowledge is simply essential. So our project is addressing this pressing issue by bringing together 16 countries, summing 20 partner institutions. And we're focusing on 2 cross-border case areas that you see there in green: Route to Rhine and Pannonian Basin, and 2 one-country pilots that you see in blue: Ireland and Bavaria. And we all together work towards the goal to provide geological knowledge in an understandable and meaningful way to help bridge this gap between scientific knowledge and policy needs. So we are doing this through the structural framework model. And if you don't know exactly what it is, today, hopefully after this webinar, it will be much clearer. But just to introduce it very briefly, you can think it as a 3-pillar model. So to start, and very important when discussing geology, we organize information in different map layers, which represent the fundamental structures and the main building blocks that define the subsurface, which we call limits and units, respectively. And on top of that, we add geomanifestations representing past or ongoing subsurface processes. But each of these layers is not only made of spatial data, but also of a database and a vocabulary connecting many types of information. So geological properties, references, definitions, classifications, and relations between each single element in the model. So the result is a robust integrated model that represents a snapshot of current geological knowledge about a region. So today we would like to show you a bit of this structural framework model and some of the results that we have, and of course get your opinion on them. But before we dive into this, Isaline Graveau from the French Geological Survey, she will start by giving the context of this main challenge that we face, the challenge of subsurface management. So, Isaline, I will set up your screen share in a moment.
Thank you.
You should be ready to go.
So, can you see my screen?
Yes, it's great.
Perfect. So, hello, good morning, everyone. I'm Isaline Graveau from BRGM, the French Geological Survey. I prepared this presentation in collaboration with Monika Koneczynska from the Polish Geological Institute. And I am so starting this session of the GPS event dedicated to the GeoConnect3d project with sharing with you the review conducted in one of the work package of GeoConnect3d about subsurface management. So the subsurface plays nowadays an important role as it provides essential resources, drinking water, hydrocarbons, raw materials and heat, etc., as well as also the capacity for large-scale fluid storage, natural gas, liquid or liquefied hydrocarbons. And also for some activities such as raw material exploitation, the use of underground resources even already has a longer history. These maps on the slide, maybe can you see my mouse here?
Yeah, we can.
Okay, also I can point, yes. So these maps were built in the GeoConnect3d project, collecting information from the partners of the project. So you see only the country that were involved in the GeoConnect3d project. And we collected information about the uses of the subsurface in their country. And so for mining resources, oil and gas, geothermal waste disposal, hydrocarbon storage. And you can see that some exploitation have a long history, and some are really rather developed during the last century. In green are the countries where no type of this activity is not developed or is not anymore conducted in the country. For example, for mining in France nowadays, there is no active mines, but in the past, there was a huge mining activity, for example, for coal. So this slide shows you that there is nowadays a real a crucial role of the subsurface in our lives, in fact, in our economies. And also the use of subsurface is expected to increase in the future, to increase even more, mainly because of the energy transition, with new types of subsurface issues adding to the existing ones. Among these prospective uses, we can mention the storage of energetic vectors such as compressed air, hydrogen, methane, etc., or waste, or also of CO2, of storage of heat, and also new types of mining or energy resources exploitation. So this raises also new challenges and potential mutual interactions with potential combined impact, long-time effects, question about responsibility, control measures, and remediation action plans. So the question arises, so we can observe the increased use of subsurface as well in the last decades, and also in the future with all the prospective uses I mentioned. And the question arises as to whether these new uses would generate potential conflict in the utilization of the subsurface, what would threaten the economic or technical viability. Indeed, despite the vastness of the subsurface, only a fraction is suitable for above-mentioned uses, and many of them target the same geology, thus potentially generating a conflict of use of the same space. So we can foresee interaction between subsurface uses. So I already spoke about a conflict of uses, but we can also foresee means of positive interactions that can be reuse or synergy between uses. So about conflict of use, there is a conflict when the interaction between two uses are negative interactions. That means one application prevents the settlement of the other or its economic earning. But the conflict of use does not necessarily concern simultaneous operations. For example, the setting of a particular subsurface use can prevent future utilization of the area for another subsurface use. We can mention direct conflict of uses when two subsurface use target the same underground volume, but for different applications. So, for example, this is a map of France with potential for geothermal, because geothermal is targets the main deep saline aquifers in the sedimentary basin in France, which are mainly the Paris Basin, the Aquitaine Basin, and also the southeast Rhodanian corridor and basin. So there is also these are the deep saline aquifers that are also targeted for CO2 storage. So, for example, these two potential uses target the same geological formations. So this there is a kind of competition that occurs at planning and permitting stage, and so we have to choose one of the possible uses for this subsurface porous area. But we can also have indirect interaction between when the influence radius of subsurface activity reaches the influence area of another subsurface activity in the vicinity. For example, in pore space applications such as storage, a pressure impact can reach another subsurface activity. So I will provide an example using the Lusanier and Isotte gas storage in the south of France here. So there is at Lusanier and Isotte a vast seasonal gas storage, which generates seasonal pressure variation in the aquifer, as you can see here, depending on the volume of injected or produced natural gas. And also a pressure impact is observed in wells several tens of kilometers away. As you can see on the map, all the pink dots are wells where a pressure impact is observed. As you can see here on the graph, the pressure variations follows the pressure, the cycle of injection of natural gas in the Lusanier and Isotte storage. So also In the area, there are thermal stations which have pressure impacts that are around 20 kilometers away from the storage site. And for example, they have some spring rates decrease, but only pressure impact and no chemical impact. And also there are some wells for water exploitation and drinking, or for drinking or irrigation, that also present a pressure impact, but that can be resolved by installing pumps. So this was about indirect interactions between subsurface uses. And we also can see that some subsurface uses can be complementary to each other, and interactions can be other positive interactions. So we can speak about reuse when the later activity use the effect of a former one, such as using salt cavern left after salt production for storing fluids, or using depleted hydrocarbon reservoirs also for storage purposes, or using old mine shafts for pumped hydropower installations, etc. And synergies can also be found between two projects in ground space that are simultaneously complementary, such as injected waste acid gases into hydrocarbons trap to sustain the exploitation pressure, and also recovery, heat energy recovery from production water. Here is an example of an abandoned mine in south of France, Gardanne, where the largest mine well, which is now flooded with water. The water is used for heating, cooling of an eco district. So this is an example of reuse. So this brings me to the concept of subsurface management, defining this concept and the needs. So subsurface management, we mean it as a term which covers all considerations, planning, decisions, and actions to allocate specific uses to appropriate subsurface location. Management process should include prediction of complex and interacting effects on targeted space, for example, the storage formations, also on neighborhood, the formations in close vicinity, and also on protected compartments entities like groundwater, soils, ecological functions, and human well-being also. And to successfully employ the subsurface system, we have to consider the possible mutual interactions of intended usage options with other existing or planned uses of the subsurface. The idea is to optimize the use of subsurface, including or avoiding, in fact, resolving the conflicts, and also looking for potential synergies, and maybe inventing some synergies that we are not have not been set up for the moment. And such approach requires a complex recognition of natural conditions with regard not only to a particular use, but with a careful assessment of overall possibilities. Because features often omitted or ignored in the past can play a significant role in a proper evaluation of accessible space. And I also want to point out the importance of temporality. I mean, taking into account the time aspect, because I already spoke about synergies by reusing abandoned cavities. So trying to optimize the former uses of the subsurface, but also have a look on the future having a long-term management addressing the future uses of the subsurface or the future possible uses, as well as the current ones. For example, setting a particular use at a particular place may, in the future, prevent for another exploitation in the same area. So we have to think about the future and what the consequence of our actual decisions on the future. So I move on to the regulatory framework in Europe. This is a work that a review that have been conducted by the PGI team. Among the partners of the project. So it appears that at national level, there is a diversity of authorities and competences, even inside the countries, for questions regarding to the subsurface management. And also when comparing countries, between countries, there are some differences in organization. So there is no single pattern, or at least single approach of managing the underground space. None has incorporated the subsurface management issue in a legal system. And we identified also inconsistencies in regulations that create either lacks or overlapping of competences. And we also identified a lack of consistent subsurface use registry. And the main observation was at national level, the approach of subsurface is project related. That means that subsurface is not considered as a resource itself. For example, in Poland, there is no underground activities that can be permitted within protective pillars of documented mineral deposits. Regardless, it cannot affect mining activities or protective functions of the pillar. In Germany, the present version of the mining law allows only for one type of subsurface utilization per license area. And also I can mention the general ban for hydraulic fracturing in France, Ireland, Bulgaria, and also temporarily in Germany and the UK. What about the EU level? The regulations related to subsurface uses are dispersed in various directives or decisions. For the moment, subsurface is regarded as member state national competence. So we think there is a need for an integrated approach of subsurface management as a whole, and not only for shallow urban applications in which subsurface management is already being studied, but also for deep subsurface and the subsurface as a whole. I took this scheme from the ESTMAP project for energy storage, but it illustrates well all the possible multiple uses of subsurface and deep subsurface. So our closing remarks on the subject are that the subsurface ought to be recognized and defined, not with regard to a particular project, but independently, the subsurface independently and as a whole, to characterize its potential for multiple uses. And the former approach, out of sight, out of mind, and first come, first served, are no longer possible. And because of these multifunctional opportunities, as well as the fact that the subsurface has no borders, its sustainable use will require a wide cooperation of a number of authorities on local, regional, national, and international levels. So in the same way of thinking, having a common way for managing subsurface use in the neighbor countries would help to set up transboundary agreements with a special transboundary procedures which slow down process and generate conflicts. There is a strong need we identified for creation of an understandable terminology, which scientists, engineers, constructors, decision makers, policy makers, and citizens may understand, and which could be used for better communication between all groups. And last but not least, there is also a need for a new generation tool providing knowledge to all interested parties. So this brings me to the developments carried out in the GeoConnect³ project, the structural framework, which Renata already started speaking about. The idea is that complex geological model and large quantities of subsurface data make it difficult for non-geologists and stakeholders to identify areas for promising subsurface development. So geological data are to be simplified and organized so that non-geologists can interpret and understand the data. The GeoConnect³ propose a new approach, the structural framework that will be presented by Chris Pissens shortly after my presentation. The other concept are geomanifestations. So the idea is to derive knowledge on opportunities for subsurface use through utilizing visible phenomena on the subsurface. So GeoConnect³ proposed to use geomanifestations for interpretation of the subsurface, and this will be described by Joanna Vandel also just after. So the methodology developed in GeoConnect³ project combines both concepts. And finally, I know address to stakeholders, because we really need stakeholders' feedback. We are eager to hear from you about subsurface uses, especially about your awareness of the necessity of subsurface management, and to hear about the challenges you face, the real-life feedback and the experience, and also your needs in terms of subsurface management and planning, and of course feedback on the approach developed in the GeoConnect³ project, and that will be shortly presented in all the presentation after. So please, I will now ask you to answer the following polls that Renata will explain, and also do not hesitate to post questions and comments about this subject. So if you want to contact us, me and Monica, to exchange with us on this subject. So thank you for your attention. I know I give the floor back to Renata.
Thank you so much for this introduction, Isaline. And now, as Isaline said, we are eager to hear from you, or read from you in this case. So I invite you to use the link that you can see in your welcome message on GoToWebinar, or you can go to paulev.com/GPS888. So we have a few quick questions for you with this presentation from Isaline in mind and from your own knowledge. So the first one, and you can add as many keywords as you like, is which keywords come to your mind related to subsurface management issues in Europe? So I will not show it for now. I'll wait for a few words to come in. And in a few seconds, we will show how these keywords come together. So I see a few results coming in. I will show how it looks like for now. So there's a nice variety of different keywords for now. Yes, so far there is a range, but yeah, it seems that issues is a frequently added word. Conflict, legacy. So that's very interesting to see these results. Because we have some other questions, I will now move forward. But these questions will be available as well after the webinar if you want to give more input. So with issues and legacy still frequently mentioned, I move to our next question. And please tell us, how do you agree with this statement? Subsurface management is a key issue in the development of the energy transition in Europe. So you can go anywhere from strongly disagree to strongly agree. And again, I will wait for a few results to come in before showing the results. Okay, I will show the responses now. Seems we have a majority in the strongly agree. And we in GeoConnect3d, of course, we're also in this side of the agreement. So seems mostly agree or strongly agree with this statement. Okay, that's great. I think we don't have any more answers coming in. I move into third question. And this is an open end, so you can write freely. But we ask, which concrete examples of subsurface management issues do you know? These might include conflicts of interest, synergies, policy changes, and so on. And for this one, well, I show already if we have anything coming in. We know this. This is not a straightforward question, but this one will be open a bit longer. I see if we just have a few coming in at least, but this question will be open for your input while the next presentations happen as well. So we have a few answers already. Thank you very much. So geothermal, CCS, aquifers, geothermal and storage. So these are very good examples. Thank you very much. And as Iselin said, we're collecting feedback from you today, but also from a range of stakeholders, because this helps us to move forward in this last year of project. So I thank you very much for your input. I know that we're running already a bit behind schedule. So this question, this poll will remain open if you want to continue writing. But now I would like to move on to some results of GeoConnect3d. And we'll have two presentations about the structural framework, starting with a brief introduction by Chris Piesens, my colleague from the Geological Survey of Belgium. So Chris, I will stop sharing now and you should be all set.
Yeah, thank you, Renate. Hi, everyone. As this title suggests, it's going to be a very short presentation, just as an introduction, more or less, to the more detailed presentation that will follow And it's really about, we're still going to stay here at the level of Europe, pan-European geology. And the question is, how do you visualize that? And of course, if you just look down on the Earth, you already see some geology, like you've got the Alps here, the Pyrenees, and if you really, or the coast of Norway, if you really look more in detail, you know the geology, you can already make out some more particular structures like Pannonian Basin here. But all in all, this is topography. And topography, yes, is influenced by geology, but it's not geology itself. So if you want to talk or look at geology, how do you do that? First thing that you would always have done, certainly up until 2-3 years ago, is put a geological map on that. Problem with the geological map is that it's very colorful, but at the same time very complex. No, we didn't include any, not even a scale, not even a legend here, but even if it was there, it's quite a puzzle to get through. And on top of that, it's also quite challenging to create these kind of maps. This is the IGME 1.5 million across Europe, and which gives you a nice overview. The more you zoom in, the more difficult it gets to actually produce harmonized, nicely uniform geological maps where you don't see the borders where different surveys have been mapping next to each other. So it's a nice attempt, but we think we did something, or we actually want to challenge this and come up with something new, and we call that the structural framework, which summarizes geology in a different way, at different scales, for different audiences, for different disciplines and topics. So what I'm going to do now is give you, in a couple of slides, maybe 2 minutes, an idea of how the geology of Europe looks like in very broad outlines, without using a geological map, but by using a structural framework. And if you look at geology that way, let's forget about countries as well. I'll just point out that, well, UK will be somewhere here, Brussels will be here, and here you've got the map with Italy and Spain here and Baltica there, or well, the Baltic area. Now, what first thing you need to know about Europe is that it's a collection of pieces. So, and the oldest core is here, and through time, each time new pieces have been added from the south. Basically, it's split up from Africa or whatever the continent was named before that. And what we see here are actually the lines, the limits between these different fragments and pieces. Obviously, we can color these pieces a little bit in order to get a bit more visual appreciation of the whole thing. But you see, it's really, especially from this line on, and this is, like I said, this is Scandinavia here, it really becomes an amalgamation of different lines. If you know a little bit about geology, you know that if two plates, even if they're relatively small, collide, you get an origin, you get a mountain building. You will see that along each of these blue lines, you've got, well, these are again limits, but these hatched areas are each time and largely overlapping different origins that have been originated from time. And again, the oldest ones you find here, the most recent ones, even the currently active ones, like the Alps, are down here in the south. And you see immediately that a large part of Europe has, if you go deep enough, not necessarily the most recent sediments at the top, but certainly the deeper ones at the bottom, you will find deformed rocks there. Once this has all been accreted, it becomes one new continent, and a new continent does one thing, break up again. And you can already see that in Europe as well. You've got here these different rift systems. This one is in North Sea, this one is the Rhine area, and it actually extends all the way to the Med. These are different rift systems in Europe, and you see that these new systems actually cross-cut the older geology. They largely neglect the older sutures, and they just develop like this is one uniform block. One thing we didn't yet indicate, which is however very important, is, well, you've got continents and you've got oceans, and they are they're completely different in geology. And this is drawn by this green line here. So UK will be somewhere here, but actually the continental shelf, North Sea, is still continent, and you have to go outwards before you actually come into what we call geologically the ocean, with Middellandse nicely situated here, and Iceland would be here. Iceland is not a continent, it's actually just a piece of oceanic crust. So that's the geology. Now at this level, structural framework does, and you see immediately I've got piled up a large amount of information here. We can even add on more. We can start giving more details, more names, etc., etc. But I will not do that here. I will leave that for the next presentation. Just tell you something about the different areas that we have that we've got covered here in the next presentation, also by the project. One thing I want to point out as well as this, that I'm talking about this, and that was really the goal also of the structural framework, about being able to use it in a very intuitive way. But don't be fooled by that. At the bottom of this is a very fundamentally very rigid methodology, and there is a very nice report, public report out on that, on detailing how you actually should document, detail, and summarize all of this information so it can be used as a structural framework. But that's not, you will see some elements possibly in the next presentations, but the goal is here to talk about geology. Now, I said the different areas that we were looking at. The methodology you saw before, this has been developed by the two major areas, which we call the case studies, Pannonian Basin here and Ruhr-to-Rhine area here. But in order to, what we also want to test in the project was, if we develop a methodology, can it just be used by another partner? Because that's something that very often is not proven inside a project. And that's why we have two pilot areas, Bavaria, which we will not talk a lot of today, but also Ireland, and that's going to be the next presentation. Ireland just took the methodology when we were ready with it and implemented it to document the geology of Ireland. As I said, that's going to be the next presentation. And Ireland is a very nice case. It's not that simple, the geology there. Ruhr-to-Rhine, for the other ones, you will see something of structural framework, but they will rather be talking about geomanifestations. But just geology-wise, Ruhr-to-Rhine is not a geological entity. It's not even a geographical entity. It's just an area that we chose as something that is really challenging to do, to come up with one uniform, harmonized geological model. And as you see here, it really crosses about a lot of different terrains, a lot of different structures, a lot of different geological domains. Then here's the Pannonian Basin. Pannonian Basin, actually, like the name said, a very recent basin, but you will see there that the geology, they didn't just stop at the basin infill. They actually focused quite a lot on what you see here. That is a deeper geology, the basement of that basin. And as you can see here, that's quite complex in itself. So I'd like to stop here and give the word to the next speaker.
Thank you, Chris. And I will then move forward to Russell Rogers from the Geological Survey Ireland. And if you're wondering the application of the structural framework to a whole country, he will show you the result. So Russell, we still cannot see you. No, we see you, and I will give you the share screen, and the floor is yours.
Hi, thanks, Renata. So to follow on from what Chris was saying, we were given a very rigorous methodology to produce a structural framework. But within that, we still had to make decisions at every level of what we wanted to show, how we were going to produce the structural framework, and what features we would include or exclude. So I like to think of the structural framework as a pre-interpreted geological map. So our structural framework is a whole island of Ireland framework, and we've produced it from existing mapping. So it covers 3 different zoom levels, and this largest zoom is produced from the GSI's 1 to 1 million map with elements of our 1 to 500,000 map. And we've used the collaborative GSI and BGS 1 to 2.5 million map to fill in the geology in the north. And this level, it kind of shows the main structural features and the structural grain of Ireland. And you can see the major intrusions and various inliers. And there are 3 different types of boundary that we've used throughout all the levels of the structural framework. So these would be the unconformities that have dots. just general contacts, either igneous or stratigraphic contacts, and faults. So as we move down into the next level, you can see more detail starts to appear. You can see the Carboniferous has been subdivided, and you can see more details in these inliers. So for the Carboniferous, this was a major decision point for us. Did we want to show the structural framework units by age or another feature? And what we decided to do was to show the major Visayan basins and shelf facies, as these are kind of in line with the general structural grain of the country. But there are many other ways we could have chosen to done this. So you kind of have to think of this structural framework, or the way we've come to think of it is, this is a structural framework to look at the major structures in Ireland. If we wanted to produce a structural framework for a different reason, then maybe we could have made different decisions in how we displayed the Carboniferous. And then we also have a third zoom layer as you come in. This layer is developed from our 1 to 50,000 mapping, which we don't have national coverage of. We only have it in a few areas. And we chose 2 areas to show this most zoomed in level based on where we had developed 3D models from the Hotline GeoEra project. So we have a 3D model in this area, and we have another 3D model I'll show in a minute. And this can just show a few more facies distinctions in the Carboniferous, and it can also show more detail of the structure that we wouldn't be displaying at this zoom level because they're not the major basin forming faults. And the other area is Loch Allen. We also have a 3D model here. Now here, we're not really displaying facies. This is by age, which is controlling the facies as well. And as I say, we've made the decisions as we've gone through, and we've had to make a variety of different decisions, but these are all really well documented in the methodology. So accompanying these spatial data, there's a really detailed vocabulary and attribute table, and that will really make clear which decisions we've made. And then maybe not why, but it will make clear which decisions we have made. So the next thing I want to show you is just 5 examples taken from the structural framework, which I think highlight key differences between the structural framework and a geology map. So first of all, I just want to show how the structural grain of Ireland is displayed much more clearly on the structural framework than it is in the geology map. So on the left, this is our national coverage 1 to 100,000 geology map, and it's very busy and very complicated. And there is an awful lot of information in there, and the geology map is by no means obsolete, but you do need a certain level of understanding and experience to interpret it properly, to actually extract the value and the data from the map. And then with the structural framework, we've already taken those steps for you. So we've extracted information from the geology map and made it very clear. And you can see that Ireland is dominated by these northeast, southwest trending faults for the most part. And so I think that's a key advantage of the structural framework at this scale. Another feature I want to show you, this is an example from Ireland here. If you look on the structural framework on the right, you can see these faults dominating, and this is a basin and shelf facies in different basins. You can't see that on the geology map at all because you have these much younger Numurian sediments completely covering the Visayan basins. And the main feature you pick out on the geology map is this kind of north-south undulating unconformity, which is where the younger sediments overlie, and it just completely obscures any of the basin and shelf that you might want to see. So where we wanted to show the Visayan basins, they're clearly visible and obvious features on the structural framework, but you would need a lot of work to extract that from the geology map, and you would need to look at cross sections, and you'd need to read the accompanying literature, and you'd need to know the geology of Ireland to understand what's beneath this. So I think that's a very key feature of the structural framework. So another example here, this is again showing the simplified pre-interpreted nature of the structural framework. This geology map here has, I know from working in Ireland and from looking at a lot of geology maps, that this is a big unconformity, and there's a big inlier here, much older sediments overlain by these Carboniferous. But when you look at the contact, it's very faulted, it's a very complex contact. But when you look at the structural framework, we've really simplified that out and said it's dominantly an unconformable contact. And that is really clear that this is an inlier in unconformable contact with the Carboniferous. But from the geology map, you would need to work and interpret to discover that result. And a similar feature here, the geology in North Dublin is complicated, and you would need to work to determine that this is a faulted block of older material in the Carboniferous, whereas on the structural framework, it's just apparent from looking at it, and from looking at the vocabulary, you would just know that. And the same with this inlier, this outlier here of the Carboniferous. It's just clear there's an unconformity that's faulted on one side, whereas from the geology map, you need to work to extract that information. And again, here in the Carboniferous, you can see really clearly that this is a shelf facies, this is a basin facies, this is a different basin and a different basin. But from the geology map, you need to look at cross sections, you probably need to look at drill holes, and you probably need to read a lot of literature to extract that information, whereas the structural framework has done that heavy lifting for you. So that's a brief whistle-stop tour, and I'll just go back to show off the visualization of the structural framework, which I think is really very nice. You can zoom in and you see details beginning to appear, or you can zoom out to lose some of the detail. And that's what I have to say about the structural framework of Ireland. I know I'm a bit ahead of time, but maybe there's some time for people to ask me questions. I don't know, Renata.
Thank you very much, Russell, for showing us the application of the structural framework. We are still waiting for questions. There is a bit of a delay as well with the streaming. So you in the audience, we ask you to send your questions through the Q&A box. Maybe while we wait, if there are any questions for Chris and or Russell, we also would like to hear your opinion about what you've just seen of the structural framework. So we will ask you or open a few more polls and then maybe go back to any open questions. So thank you once again, Chris and Russell, for showing these different applications of the structural framework. And I invite you watching to go back to poll everywhere. So again, the link that you have in your welcome message, if the link is not working for you, it's there on the slide as well, pollev.com/GPS888. So to start, we would like to know, how do you agree with the following statement? The structural framework approach is a useful way to constrain subsurface geology. And you can be honest, all answers are anonymous, you don't need to worry. But you can tell us where you are between strongly disagree and strongly agree. Once again, I wait for a few answers to come in before showing the results. So we're almost at 10 answers. Let's see the responses. We have quite a lot of agrees, which is very nice for us to hear. And of course, there's very limited time to demonstrate how the structural framework looks like and how it can work. So this is a very positive outcome for us. I see if any other answers come in. If not, okay, it seems pretty stable now. So I move to the next poll. And that's more straightforward, yes, no, or no opinion. Do you think that the structural framework has potential application in subsurface management? So mixing a bit of what you've seen demonstrated in our opening talk of today. So I just wait for a few seconds before showing the results. And we're almost reaching 10. Let me show. For now, all yeses. And once again, if you haven't joined the polling, you can do so with the link in your welcome message, or just copy the link from the slide. Okay, we have a strong yes, which also makes us very happy, of course. So it seems stable for now. I will move to our final question of this block. And this again is an open-end question. What aspects of the structural framework visualization would you like to see improved to make it straightforward to use? And I should also mention that the final product, excuse me, will be part of the EGDI platform of the GeoEra, the whole GeoEra program. So we cannot demonstrate the final working platform for you yet, but I think from what Russell has shown, you can already have an idea of how this works. So this is an open-end question. Feel free to share your thoughts. We know it takes a little while, so this question will be open as well throughout the next presentations. Yeah, we see what about 3D? Very good question that we can discuss later on. The aspect of timing, too short to respond to, it's true. With the limited time, it's difficult to form an opinion maybe. Environmental impacts. So keep your ideas, suggestions coming. They're very valuable for us. But for now, I leave this one open. And we move forward to the second block, more focused on geomanifestations. And to start, I invite Johanna van Daal from the Flemish, wait, I will not pronounce the Dutch version of the name. I'm sorry about that, but the Flemish Planning Bureau for the Environment and Spatial Development. I hope I got this right. And Johanna will introduce the concept of geomanifestations to us. So Johanna, I will send you the screen share, and you should be ready to go.
Okay, I hope everyone can see my screen.
Yeah, it's okay.
Excellent. So in this brief presentation, I will introduce you to the concept of geomanifestations, which was one of the second part of a GeoConnect3d project. It's probably a term that most of you have not heard before outside of this project, but it's actually a very cool concept. Geomanifestations are in fact anomalies. They are anomalous geological observations. And this can apply to basically any geological subdiscipline that you can think of. And so for the GeoConnect3d project, we investigated many different types of geomanifestations. So the two most widely occurring geomanifestations that we investigate were related to water, being first of all the occurrence of thermal water. So with 3 examples shown here, it's like the thermal springs in Aachen, the Felix baths in Romania, and Pechelbronn in France. And the second one being the occurrence of CO2-rich water. And mostly this is not visible and it's just like a normal spring, but sometimes this CO2 seepage is expressed as moffets, like here in Slovenia and in Germany on the left side pictures. Or sometimes more spectacular as a cold water geyser, like the geyser of Andernach, also in Germany. But geomanifestations are not like limited to water-related observations. They also cover the disciplines of geomorphology, like this Dolien in the Netherlands, the field of mineralogy, like this lead-zinc ore mineral assemblage from the Weser area in Belgium. Also, seismic data can reveal anomalous signatures, and natural oil seeps are also quite exceptional and interesting. And so this seems like a very diverse and super variable collection or random collection of pictures that I show you in this slide, but they actually have one important thing in common, and that is that they are really indicators of a distinct process that was going on or is going on in the surface or at depth, at the surface or at depth. And so in that way, they provide us valuable tools to get to know our subsurface better. But why exactly do we care about geomanifestations to get to know our subsurface better? Well, first of all, geological data is usually very sparse, and because it's expensive to gather. And on top of that, it's also most often collected in the framework of a project. So it's very depending on the scope of the project, which data is collected and with which quality it's collected. So this results in a high variability of data coverage. And in the GeoConnect3d geomanifestation database, we actually combine all these different types of geomanifestations, and in that way we connect, in fact, the multiple geological disciplines. And so this together gives us an innovative and cost-efficient approach to explore the subsurface. It also gives us guidelines for further research. It can point us to areas that are maybe interesting to investigate in more detail. And last but not least, these geomanifestations, they provide an excellent communication tool for the general public. I think the previous slide showed it quite clear. And then to go really into the topic of subsurface management, which is the theme of this morning's workshop, geomanifestations are of a great support to deal with subsurface management issues. As I already told, they represent a unique combination of cross-thematic data, and it's quite easily to expand the data collection into a cross-border database. And they can be linked to a structural framework that was presented earlier. And so all this together can give us new insights on subsurface characteristics, for example, its structure or the lithological properties of a certain unit, and also on the key processes that are playing in the subsurface. So, for example, regarding fluid flow, gas migration, heat distribution, and so on. And so this new insight, this new knowledge on the subsurface, on its characteristics, on its processes, this allows us to make more knowledge-driven decisions. And this eventually will result in a more safe, more efficient, and more sustainable exploitation of our subsurface. And so in the next presentations, some nice examples of geomanifestations will be shown, and also how they will be illustrated, how they actually support subsurface management challenges. So both for the Ruhr terrain area and for the Pannonian Basin.
All right, so we directly move forward to hear from Helga Verket, colleague from Johanna, from the Flemish Planning Bureau for the Environment and Spatial Development. And she will present about policy questions that can be answered with geomanifestations. So Helga, you should get your notification and be all set.
Okay, you see the screen?
Yeah, all good.
So hello everyone. I will present results from 3 different teams and show some results of both the structural framework a little bit and then the geomanifestation exercise that was performed in the Ruhr terrain study area. And that's an area covering parts of Belgium, the Netherlands, Germany, France, and Luxembourg. And we will not focus here on methodology, but rather bring the results from the perspective of what they learn us for some specific policy challenges. Oh. And I have a problem. I will try to reshare the screen. Oh. I will try to restart the presentation because it was not continuing for me. I hope everything is okay for you. Yes, you okay?
Yes.
So I can switch to the next slide now. Perfect.
Thank you.
It was not working for me, so then I cannot see the animations coming. So let's go ahead with the structural framework. As you can see, on the highest level, we mainly defined units and also some very large scale fault structures. And when we zoom in, you see that the large scale structures are now replaced by more fault traces. And even in the zoomed in images, you see faults that cross the border between Belgium and the Netherlands. So it means that the geometries they stem from completely different geological models, but still they are harmonized across the border by linking them semantically using the vocabulary structure. And if we zoom in even further to the scale 1 to 500,000, you see the true complexity of the area coming through. But even there, on the smallest level, the faults are still semantically structured and remain harmonized across the border. And I think hard work that has been invested in harmonization and building an unambiguous fault model for the Ruhr Valley Graben pays off also for policy needs. Because understanding the role of faults for fluid flow and seismic hazards, for example, that's an issue for almost all subsurface activities. And it's not only faults crossing the borders, but also aquifers, geothermal reservoirs, hydrocarbon reservoirs. They don't stop at the border. So if you want to evaluate impacts and interferences related to subsurface activities, yeah, you can't use models to predict the impact that stop with the geology at borders of countries. So I really think that the structural framework can have benefits for policy challenges. A wide set of geomanifestations has been collected in our study area. Peter worked on seismic data, identifying both collapse structures and also the presence of geofluids. And you will hear more of that later during this talk. Then VPO focused on thermal anomalies, on CO2 seeps and presence of helium, relicts also of volcanic activity. And the Geological Survey of Belgium also worked on CO2 seeps, but also on seismicity data and on the distribution of polymetallic veins. And in the rest of the talk, you will hear about two concrete policy challenges. One is identifying geothermal resource potential, and the second one is understanding the migration of gases through the subsurface. So I'll take you along for the first policy challenge. The questions that we want to answer are, is it possible to predict potential? Can we identify sweet spots for preferential exploration? Is it possible to learn from well-known examples at a remote place and then extrapolate insights to areas where you only have poor indications? And good to know for you is that we defined thermal anomaly as those surface manifestations above 12 degrees C, either the ones that were never freezing, even not in hard winters. And at depth, we use these manifestations, for example, in boreholes, where the temperature exceeds the expected temperature based on a geothermal gradient of 30 degrees C per kilometer. Most of the thermal anomalies, so the red circles, cluster along grabens and along large river valleys. And of course, one would expect to find a nice potential also in the Eifel region with its young volcanic activity, but that's not the case. Unfortunately, this area shows only few and also weak thermal anomalies. What really pops out from the global overview is a strong correlation with topographic differentiation, or that means with a strong hydraulic gradient. And this gradient, of course, is the result of the highest elevation and the depth at the base of the sediments. So it means that grabens filled with unconsolidated sediments and flanked by elevated shoulders create, of course, excellent conditions for deep groundwater circulation cells. And that's something that directly pops out from this map. And the core of the volcanic Eifel lacks strong hydraulic gradients. That's just one of the reasons why you don't find a better potential there. So let's have a look to the Upper Rheingraben, which is the geothermal hotspot, let us say, of Western Europe, with a series of successful EGS projects situated at the west side of the Graben. And understanding this well-studied setting could help in predicting potential maybe elsewhere. So the location of the cluster of successful EGS projects can be explained by an efficient topography-driven flow with the Black Forest in the east, the higher elevation, and the Vosges Mountains in the west. And that creates an asymmetric deep circulation cell with strong positive temperature anomalies in the west part. And of course, in order to keep the thermal disequilibrium, fluid flow needs a rapid channeling to keep the temperature. And this is realized here thanks to an efficient 3D fracture network. If we zoom in more on some localities, we often recognize linear trends. And such is the case, for example, in Wiesbaden, which is situated at the end of the Upper Rheingraben. And here a series of surface springs is pretty much aligned. The highest temperatures are found in the northeast. It's situated along a transmissive fault. And if you go away from this fault, you see a temperature decrease. And there is also a second fault crossing the first fault with an influx of very cold water in this case. We go now to another example, much more to the north in the city of Aachen, which is quite similar. Again, you see two series of warm surface springs aligned along Variscan thrust faults. And a graben-related fault cuts these former faults. And you see in this case that both the temperature and the geochemical anomalies increase in the direction of this graben-related fault. And here the geothermal play can be explained by topography-driven flow through permeable layers in Variscan thrust sheets, what's shown in the figure to the left. And secondly, by focused upflow of hot saline fluids along deep-seated faults. So we get a combination of large volumes of water circulating and mixing with a focused heat flow. Starting from this example, we will now examine the surrounding area and see if we can predict or not. So we start in Aachen, and we will follow the same graben fault further to the north, where we arrive in the Netherlands. And here in the past, we found an outbreak of a 50°C hot brine, which was encountered by accident during the coal mining. And if we go more to the west of this graben fault, we see a series of weaker anomalies, both at surface and at shallow depths in the Netherlands and in Belgium. So again, we see a decrease of temperature when we go away from this deep-seated fault. If we use this knowledge from these two processes identified, we see that we can predict spots with a nice potential which deserve further examination, I think. And I give now the floor to Bernd, who will speak also about identifying sweet spots.
Yeah, good morning, everyone. I'm Bernd Rombart from Vito, and I'm mostly working on seismic data in the Campine Basin area. So while performing seismic interpretation in the Campine Basin, we noticed that the occurrence of several seismic amplitude anomalies, and we know that those can be indicative for a fluid or a gas reservoir. And AVO analysis is actually a technique that aims to further analyze these anomalies and also detect additional anomalies. AVO stands for amplitude variation with offset, and in fact it studies the variability in seismic reflection amplitude with changing shot point receiver distance. But in order to perform such reliable analysis, we also needed to do some specific pre-select processing in order to meet these requirements of performing such analysis. And here on the left figure, you see an example, or the clearest example, the most obvious example of a seismic amplitude anomaly on this seismic survey, and it is situated within two faults which form a graben. Then, if we look at the intercept gradient crossplot, which are the two commonly used AVO attributes, where the intercept is the amplitude, or represents the amplitude at zero offset, while the gradient represents the amplitude, or the change of the amplitude, the changing trend of the amplitude with changing offset. And then we noticed that this high amplitude anomaly, that it corresponds with the class 1 anomaly, which is known from literature, and these anomalies are typical, or can be typical, for gas or fluid filled compact sandstones. And if we then see where they occur in the middle of the Namurian, then we know from nearby boreholes that within these measures that some thicker sandstones occur. Yeah, can you go to the next slide?
It's not continuing again. I will see if I can do the same trick as the other. No, still not. Is it visible now? Yep. I changed it. Okay, perfect.
This correct slide is
sorry.
Correct slide. Okay, then in general, we can conclude that that the anomalies that we noticed are mostly linked with faults, which give an interesting link with the structural framework, of course. That we know from literature that these anomalous zones can be linked with gas-rich and/or fluid-bearing intervals, and of course these are the intervals that we are looking for if we are looking or searching for zones with highest geothermal geothermal potential. So these, yeah, in that way, it's a very interesting technique to get some more insight into the spots with the highest reservoir potential. Helga, you can if it works.
Yeah, again, the problem with changing, but I find a way. So in conclusion for this first challenge, we can say that we both need a motor for groundwater circulation, which is mainly determined by the hydraulic gradient and hence by topography. And secondly, we need efficient heat transport, which is primarily through channeled flow along fault zones. And the examples that we show that cross-cutting of different fault sets can play in the advantage, but it's not always the case. And also, I think it's clear that with the very high upfront exploration risks that are typical for geothermal projects, AVO analysis can become a promising cost-effective technique to evaluate drilling targets, and by this lower the geological risk. Okay, it works. Then we go to the second policy challenge, which is about understanding how gases migrate through the subsurface. Understanding underground seasonal gas storage and also long-term sequestration of CO2 both require an understanding of these mechanisms. And the advantage of studying natural analogs like the Ardennes and the Eifel is of course the scale, both spatially but also time-wise, because you can study migration at full scale and also at a long term, million of years. And good to know again here is that for the anomalies, we collected those based on measured CO2 concentrations or based on visual observations, like for example, gas bubbling up, geysers, travertine, and so on. And also mainly based on literature data. We will go through several zoom levels and each time look to what mechanisms pop up from the analysis. If you look to the over-regional scale, you see that the blue dots for CO2 seeps and yellow ones for helium coincide largely with the volcanic fields, but they are not restricted to these areas. That's also clear. If we zoom in on the CO2 data set, we start seeing alignments of seeps along faults, and we recognize both Riscan faults, but also other deep sutures, some corresponding indeed with known faults, but sometimes also that don't correspond to any mapped faults, which is interesting, of course. If we zoom in even further, we see that the effect of the faults gets obscured, and that almost all seeps seem to relate to groundwater discharge zones. CO2 bubbles up, for example, in lakes, at the border of rivers, along creeks, in springs, and so on. And this is especially the case where faults that were first conducting the CO2 cross through an aquifer. And then the CO2, of course, gets dissolved in the groundwater and gets redistributed to the point that you get the impression that the distribution of CO2 is controlled completely by hydrogeology. But as most CO2 seeps have been identified first based on visual observations, the water in fact makes the gas visible. This creates a bias in the database. There are some dry moffats in the database, but not many, because it's not always easy to locate these dry seeps. If we zoom into the field scale, that shows the sampling and the characterization of the waters. And the origin of the CO2 can be either organic derived, it can be the result of dissolution of carbonate rocks, or it can be of a mental origin. And that's the case for example, for the Eifel and the Upper Rheingraben, but clearly for the Ardennes, it seems to be of a mixed origin. And when we talk about this bias in the database, by focusing mainly on wet seeps, yeah, we could look to alternative mapping methods. And one that we found interesting is the use of biomarkers. Berbrich and Schreiber, for example, in the Eifel studied the structures, the mounds of redwood ends. And these ends love geogenic gases, and so they cluster their constructions on emissive fault zones. So in conclusion, for the gas migration, we can see that the Ardennes and the Eifels indeed are interesting natural analogs to study. And we see how different scale levels accentuate different migration mechanisms. And in the end, there seems to be an interplay between diffusive processes from the mantle or from another carbon source. There is focused upflow along faults, and that gives linear trends. But if these faults cross to an aquifer, then CO2 gets defaulted in the groundwater and redistributed and will reappear along the discharge zones. This was the last slide, so I thank you for your attention, and I hope you got some inspiration from the selected examples. Thank you.
Great, thank you. And now we move to our last presentation of today about the structural framework and geomanifestations of the Pannonian Basin. And Gyula Maros from the Mining and Geological Survey of Hungary will start. So Gyula, you should receive a notification and be ready to go.
Please give me a feedback if you see my screen.
Not yet on presentation mode.
And now?
Yeah, all good.
Okay, thanks. So greetings from Budapest, greetings from the fabulous Pannonian Basin. I will tell you some words about the geological background and the structural framework and so on. Then I give the word to my co-authors to speak about the geomanifestations. So the Pannonian Basin is situated here in Central Europe, surrounded by the Alps, the Carpathians, and the Dinaric Mountains. It is a plainy, hilly countryside with island mountains. I presenting you from here, from Budapest, and later on Nina will presenting you here from Ljubljana. So the Pannonian Basin is a back-arc basin of the alpine orogeny. The territory of the Pannonian Basin is shared by 8 countries, but the nature, especially the subsurface nature, doesn't know anything about this sharing. From the point of view of the geological buildup, you can see this section. The territory can be divided into 2 main parts. It's separated by this thick red line, which is made in unconformity within the Pannonian Basin. Below it, you can see the Pannonian Basin basement complexes. They are Paleo-Mesozoic crystalline and sedimentary formations. Above it, there is the Pannonian Basin infilling system, which is a volcanosedimentary sequence from the Miocene times. as far as the basement formations concerns, we built up a structural framework, and for the infilling sedimentary sequences, we made a harmonized horizon 3D model about the whole Pannonian Basin. You can see here the basement mosaic of the Pannonian basement, which is much complexer than the hilly countryside of the Pannonian basin. It built up some main mega units like the Alcapa, Tisa, Dacia, and the Adriatic Dinaric system. The blue arrows indicates the tectonic transport within these mega units. The orange arrows indicate the present state upper plate or lower plate arrangement of the different units within the Pannonian basement. So you can see that below the simple countryside of the Pannonian basement, there is a hidden and complex, a little bit enigmatic pattern of the basement rock formations. The structural framework, what we have built for the basement formations, we made in three graded scale range. The first, less detailed, is the pan-European scale, which contains mega units and dislocation zones. The intermediate scale is the Pannonian Basin scaled range, what contains the units and fault zones delineating them. And the most detailed scale is the regional scale, which contains the subunits and the separate faults. This cartoon shows you how the different scaled structural framework layers coming upon each other. On the top of the structural framework, there are the limits below the units in different detailness, and the limits contains mainly faults. These are known faults from the geological literature. Almost all the limits of the structural frameworks can be identified with these faults, but not all. So for them which cannot be identified, we made some artificial identification system for the sake of the completeness of the structural framework database. Now let's jump up a little bit higher to the layer model of the Pannonian Basin. As I mentioned, this concerns for the infilling materials, the infilling sedimentary sequences of the Pannonian Basin. This is an example seismic section on which you can see the 5 different horizons, what we choose to map on different 2D and 3D seismic materials throughout the Pannonian basement. And as a little movie, I can show you the resulted harmonized horizons for the Pannonian basement. This is a perspective view. You can see the Pannonian basement and the territory of this project from the southwest. This is the basement surface, first horizon of the model, with the red surfaces of the sub-basin opening fault system. Now I changed the basement color to pink because the basement crops out from the other horizons. This is the rift initiation and rift climax horizon. This is the delta slope base horizon, and this is the delta slope top horizon. I think we reached a good background for the geomanifestations hanging on. So after that, we can speak a little bit about the geomanifestations. We investigated the geomanifestations in 3 pilot areas. In the Muralzola pilot area, which is from Slovenia, Croatia, and Hungary, the Bottonya pilot area from Hungary and Romania, and the northern Bosnia and Herzegovina pilot area. And now I give the word to Nina in Ljubljana. Hello, Nina. Ljubljana calling.
Hi, Gyula. You hear me?
Yeah.
Okay. Okay. So thank you for the slot. You can continue to the next slide. So I will say a few words about geomanifestations, which we found in those 3 areas. You can see that 2 of them are of transboundary character. So in these 2 areas, we already identified transboundary structures, which are mostly related to geothermal resources in the past, while we added additional Bosnia and Herzegovina pilot area, where we focused, let's say, solely onto thermal waters at this moment. And what you can see from the table, even if you don't go into details, that all 3 regions are quite different. So the type of geomanifestations we could find are very diverse. In the west, which is, let's say, outcropping area of the Pannonian Basin, with also a lot of outcropping basement rocks, there is a lot of seismicity, a lot of seismic events, but also very diverse, all kinds of different thermal waters, gas seeps, and even oil and gas fields and so on. While in the east, at Batonia High, the area is much more flat. So we don't see really any surface geomanifestations. What was found by deep research, and mostly, so these are thermal and thermomineral waters and oil and gas fields, but also some very deep types like overpressured zones, which you can find only a few kilometers deep. But the others are quite rare, so no really gas emanations, little seismic events, and so on. And as I already told, in Bosnia and Herzegovina, we focused only on thermal waters for now. Next slide, please. Okay. So in this western part of the Pannonian Basin, what we could confirm is there are definitely a lot of geomanifestations, and we identified 3 main fault zones. So a lot of these geomanifestations can be linked to linear features. And the 3 main faults, which are described in details in structural framework, are slightly different. So the yellow one, the Raba, you can see there are also a lot of gas emanations, so mantle helium. There is a lot of mineral water and Moffat occurrences, which do not really occur in so many other places. While in the middle part, along the Ljutomer fault zone, we have a lot of geothermal manifestations, some seismic events, and a lot of gas structural traps, so actually oil and gas fields, which are not directly connected to fault, but really to the general planar structures of the sedimentation. On the south, there is still active periadriatic fault system. Here we also see some mantle helium. We find very special thermal and mineral waters, and definitely a lot of seismic events. You could imagine that some of these are also linked to earthquakes that occur in Croatia in this year and last year. So there is actually very much of activity still going on here. Going to next slide. Okay, so going towards east, you can see very flat area, not much surface occurrences, but a lot is going on in the deep. So what we were focused was the weathered zone on the top of the basement, which enables the fluids, mostly groundwater, with high mineralization to flow along this very topographically diverse basement zone. And here is a lot of hydrocarbon accumulations and huge amount of thermal wells. So difficult actually to research the area, but very interesting when you look at these special geomanifestations. And mostly these are planar structures. So not only point information, but a lot of planar structures as fields and aquifers. Next slide. And the north part of Bosnia has quite some manifestations of very special thermal and thermomineral waters. They are linked to a regional Spreča Kozara fault zone. So actually here we have contact between very, very different types of rocks, a lot of gas inflow, and that's why the result are very diverse waters with special alkaline or gas CO2 content, methane content, and so on. So this was one of the first, let's say, tries to identify regionally such occurrences here, and this is one of the parts which will be really interesting to some further investigation to delineated geomanifestation. And the last slide for my side. It's happening? Okay. So when we checked and tried to realize the regional processes, we mostly focused on geothermal anomalies. We used FIFLOW software in two areas, so in West Murazala Basin and in East at the Batonia High. And we did the heat and flow model, trying to observe geothermal anomalies to model scenarios. We were able to do this and we got very reasonable fit. And what we saw is actually that the thermal anomaly in the Murazala Basin occurs in the basement along the Ljutomer fault, where we get a lot of convection along this fault. So even if you want to research for deep geothermal resources, probably along this area would be the most prospecting region. While in Batonia High in the east, we were able to see how the groundwater flow is restricted to this weather permeable zone on the top of the basement, and how this affects the temperature distribution in the region. So both models helped us really to, let's say, map temperature distribution and potential areas for new geothermal resources. Okay, so this is all from my side, and I give the word to Anna Maria.
Yes, thank you. Back to Budapest with the speed of light, and I pass the word to Anna Maria Nador, who will speak about the subsurface management issues in the Pannonian Basin.
Hello, good morning, everybody. So finally, I would like to say a few words. How can we translate, or how tried we translate all these fantastic scientific results in the Pannonian Basin to real subsurface management issues? Because it is very well known that decision makers or policy makers cannot handle this very sophisticated geological information, so we need to translate them somehow. What is also known that all these different subsurface sources, what we are talking about, so mostly in the Pannonian Basin, conventional and unconventional hydrocarbons, CO2 or gas storage, and the different types of groundwater, they are a kind of competing with each other in terms of subsurface, because if we look at this diagram, we can see that most of them are found the same depth range, so the same pore space. It is also quite well known from the Pannonian Basin that some discrete subsurface uses and interactions are existing, and they are known for a long time. So, for example, the Pannonian Basin is a very well-known area for hydrocarbon exploration. So, and enhanced oil recovery is used for a very long time when we are injecting either CO2 or water into the hydrocarbon fields to enhance the production.
The audio is breaking a lot.
Again, has some decades of tradition for underground gas storage in the Pannonian Basin, which can happen in depleted gas fields, but the potentials are also deep saline aquifers. So again, this is an interaction of hydrocarbon and gas. The well-known interaction is the unconventional hydrocarbon production, which raises a lot of concerns because it is the stimulation of fields with hydrofracking and have potentials either on seismicity or on the possible contamination of groundwaters. I'll switch on the camera. Okay, is it better now? Hello, can you hear me now? Is it better now?
Now we hear it very accelerated.
Shall I continue?
Maybe if you can test again.
Sorry, no, I did not say it.
Oh yes, okay, that is perfect.
Yes, is it better now? So it's good now.
Yes, please continue.
Okay, so I then. Okay. Sorry for this technical interruption. So I don't know how much you heard, but I guess this slide shows quite clearly that what kind of already existing interactions we have. And we also have some good examples also existing. For example, when we reuse abandoned hydrocarbon wells and put deep borehole heat exchangers. This is quite a recent project in Hungary and a very successful project. So what I wanted to say that these puzzles exist all together. And if we go to the next slide. Okay. But what is still missing, that how can we put in a kind of integrated framework all these different subsurface use types? And what is the new in this project, that we tried to introduce a kind of integrated assessment methodology, what we call the traffic light model. And the essence of this model is that we try to characterize the subsurface pore space in maps with a simple red, yellow, and green coloring, showing the red areas where there is a competitive use of the subsurface, the yellow, which is a kind of some competition may exist, and the green, which is not competitive. And as you see, there are quite obvious competitive subsurface uses. So for example, the conventional and unconventional hydrocarbon is definitely a competing pore space use, for example, with the gas or CO2 storage, because these are using depleting hydrocarbon fields, or these are definitely competing or overlapping with the classical thermal water systems, because these thermal waters are flowing in the same subsurface pore space. However, what is very interesting, that we found out that even in those areas where there is no competition between the pore space, so the green cells of this table, some effects might be also there. So for example, the conventional hydrocarbons are definitely found deeper in the subsurface, like the potable groundwater, which is in the shallow subsurface. However, from hydrocarbon production, if it is not done carefully, some contamination can affect the drinking water resources. So it means that it is really a very complex assessment. So we do not have to look at only the competing subsurface pore spaces, so the red areas, but we have to investigate very carefully the different effects which might be more remote and affect these so-called green or not competing pore space areas. So this was the let's say the theory behind, and now we moved further in the project, and on the two pilot areas we tried to make real, or let's say semi-conceptual models or cross sections to show how these potential subsurface uses overlap with each other. So this slide shows the Batonya pilot area in southeast Hungary, between Hungary and Romania. So probably you remember from the previous slides, here we are deep in the basin, but there is a very significant basement high. This is the Batonya high, which is built up of crystalline and Paleozoic crystalline and Mesozoic carbonate formations. And this is overlain by Neogene clastic basin fill formations. And the different numbers show the different current uses. So you see that there are the operating thermal and drinking water wells, which mostly target the, let's say, not so deep subsurface, so mostly targeting the basin fill sediments. There is a very characteristic oil and gas field in this area, which is located at the uppermost weathered part of the basement and the basin fill sediments. This is shown number 2. But on the other hand, part of this oil field is already used for gas storage. This is the Kardoskút gas storage, underground gas storage site in Hungary. And moreover, at the moment, there is a very new experimental project going on in this depleted gas field, which is looking at the future hydrogen storage. So this is really a multiple use. Moreover, there is a very recent and quite major geothermal, a new geothermal project, the Tótkomlós, which is shown by number 4. This drilling is also targeting the basement carbonates. And last but not least, there is a future project plan for deep EGS, so enhanced geothermal project, which will target the deepest crystalline parts of the basement. So as you see, a lot of already at the present time, a lot of existing and partly competing subsurface uses. If we go to the other pilot area, the Mura-Zala Basin pilot area, you see that we moved even further. So this is not a, let's say, a semi-conceptual section, but a real cross-section showing the real geology in the Mura-Zala Basin. And you also see the basement and the different basin fill formations. And the different colors show the main areas and partly overlapping areas of the current uses. Here again, you see that the uppermost part is a very important drinking water resource. Below that, you can see the main zone of thermal water convention, so where the rich thermal water sources of this area are found, which are used for balneology and also for heating. And this below that you have, but partly overlapping, you have the area of the conventional hydrocarbon fields, which are also partly used or may be used for gas or CO2 storage. And the deepest parts of the basin comprise the parts where there is a potential for unconventional hydrocarbon, or in the deepest crystalline parts also for EGS. So let's say the zonation of the uses is quite similar in the two pilot areas, but as you see, depending on the actual geology, the different overlaps can be different. So what is the next step? So I think we quite well established the concept of this traffic light models, for which the basis is an actual 3D geological model. And the next step, on which we are working now on both pilot areas, that actually to go from this 3D geological model to real scale traffic light models, where we can actually characterize the different parts of the 3D subsurface model according to this traffic light concept. So red, yellow, and green zones according to different resources and according to different utilizations. So thank you very much. I hope you could hear the end.
Yes, thank you, Ana Maria, Nina, Gyula, and also before Helga, Bernd, and Johanna for talking a bit about geomanifestations. So we are quite behind schedule, I know, but we haven't received any questions from the audience until now. You still have a few minutes to do so if you want to ask any questions about any of the presentations. But if you don't have questions for us, we still have questions for you. So I invite you to, again, use the link in your welcome message. And we have another question for you after seeing these nice examples of geomanifestations and how they can be used to answer to policy questions. So for which of these applications do you think the geomanifestations approach is most useful? In this, you can choose multiple options if you like, or if you think of something else apart from the options, you can also send it using the Q&A box. So I will show the responses so far. And we have their geothermal resource potential on the lead, closely followed by gas migration, sorry. But okay, all of them apparently you think that can be useful, or geomanifestations can be useful for them. So that's quite nice for us to see. Still the lead on the geothermal resource potential. So I move to a next question. This seems pretty stable.
Renata, we lost your audio. In the meantime, the question is on the board. So
sorry, I was talking to myself apparently. Can you hear me now?
Yes, we can.
Okay, sorry about that. Technical things are not in my favor today, so I'm sorry. So I don't know what you heard, but this question you can upvote, downvote as you want. And if you could tell us a bit of the pros and cons of the structural framework plus geomanifestations approach. Also indicate if a pro or a con. Yes, one comment there is that it's good for people with some background. which is very valid comment. Easy to communicate to non-specialists. So I wait a few more seconds. I know we are running a bit behind schedule, but I will not keep you for much longer. So I just see a question about the report of the methodology that Chris mentioned earlier. And I must say, this is not a public report, it's an internal report, but that we're preparing an open access publication with the exact same contents. But unfortunately, there's still a few months to go to share this. But of course, if you want to keep posted, you have our contact details on the website of the event. And also we are all over social media, so make sure to keep posted about the updates on this publication. So I will move on to another of these final questions. And this is about the case studies that you have seen and which were the most innovative and interesting for you. This is again an open-ended question. You can very briefly write about your opinion. I see if we have some responses coming in. And I remind you that these open-end questions, they will be available for you to give your input after the session is over, because we know it's not that easy to come up with some answers on the spot. So we have concrete examples from several countries, which we also think it's a very positive outcome of this project, of course. I give it a few seconds to see if anything else comes up. Maybe people are ready to go for a lunch break. So I would just ask you to a final question from us of what changes could improve the utility of the structural framework model with this brief overview that you've seen today presented by my colleagues. This will be open for you to give your input if you want. And for now, just to tell you once again that we really appreciate that you joined our side session today. This question will keep open if you still want to share your ideas, but I just want to thank you for joining and remind you that still the GPS event is going on in the afternoon today, talking about subsurface management once again, but with the transatlantic perspectives. And you can still register for the upcoming sessions on the website, as you see there. And I invite my colleagues to show their cameras just to thank everyone for their presentations today. And if we have any questions coming up later on that we couldn't address because of time, we will make sure to contact you. And thank you so much, everyone who presented today. And you in the audience, I hope you enjoyed the session. And I see you in the afternoon. Thank you, everyone.